boxes of equal size. Covered by boxes of equal size. Yes? And we find the number of boxes. So we have let k epsilon is the number, of course minimal number of epsilon boxes covering K. So we define the upper Minkowski dimension or upper box dimension, whatever you like to tell, of K is the upper limit of logarithm of nk epsilon divided by a logarithm of 1 divided by epsilon, as epsilon tends to 0. Of course, there is a very interesting question. We can consider upper limit, we can consider lower limit. At some times, there is a happy coincidence when these two limits coincide, then there will be simple limit. Yes. Of course, there is a temptation to give example when upper limit and lower limit do not coincide, but we will do in some break, not just now. Yes. So, if you take the upper limit, it will be upper box dimension. If we take a lower limit, then it will be lower box dimension. And if they do coincide, then we consider simply a limit of Rayleigh ratio of these logarithms, which gives us the box dimension of K. So it is this thing is discussed in the book of Kenneth Falconer, Fractal Geometry Foundation and Application, and I often use this picture. I will enlarge it. So n delta of K and the nk epsilon is the number. So we have a fractal and a number of sets, minimal number of sets of diameter epsilon covering K. They may overlap if you wish. But we need to minimize, then we minimize the overlap. Wonderfully, these sets can be replaced by balls. A minimal number of balls of radius epsilon covering K. Or minimal number of boxes which can be placed in different ways covering A, or minimal number of boxes in a grid, or minimal number of circles, non-intersecting circles with centers in K. When we pass to the limit, the difference between this number has some linear coefficients, like like if we replace the balls by boxes, the number of boxes is multiplied by maybe by 9, something like 9, or 3 to the power of n in Rn. Yes, but when we pass to the limit, this linear logarithm of this linear coefficient vanishes. Yes, this. So we have, finally we get the same number, because if you have a limit when epsilon passes to 0, logarithm m multiplied by n k epsilon divided by logarithm 1 divided by epsilon, we just write this way, right? Oh, sorry, logarithm is here up m, and we just write this way. We erase m here, put it here. Logarithm m divided by logarithm 1 divided by epsilon, but this, since 1 divided by epsilon tends to infinity, this disappears in the limit. Therefore, this changes in the size of this and form of these sets make a zero impact on the result of this operation. Therefore, we have this formula. Better to apply this formula to this case when we have boxes in a grid. Therefore, so it was a very good thing for fractal theorists. We take a fractal, put it on a boxed paper, right? Put it on a boxed paper, count boxes, and divide them by logarithm of the size of a box, and we have a very good approximation of its dimension. It's fantastic simplification of all processes, therefore it is used popularly. But sometimes it works well. Sometimes it works well. So let us check how it works in very good and very special cases like this. If so, I will keep this formula so that we could see it. And now, if k is finite, then the number of boxes is constant, independent of how small epsilon is. Therefore, we have constant n, and this logarithm tends to infinity, and we get 0. So sometimes it is denoted as Minkowski dimension or as box dimension. So we have then box dimension of k is 0, yes, if k is finite. If k is an interval, k is 0, 1, then we divide it into n parts. Each part is 1 divided by n. We have a dimension of 0, 1 is equal to logarithm n, this is divided by a logarithm n, which for sure gives us 1. Without passing to a limit, we get this number. So, okay. And if we take, say, counter set, you know, yes, you discussed it with Professor Sorab, Katyar, yes. If we have counter set, it consists of 2 to the power of n copies of diameter 1 divided by 3 to the power of n. Yes? Yes? So we have a limit when n passes to infinity, tends to infinity, logarithm of 2 to the power of n divided by logarithm 3 to the power of n can be cancelled, and we have logarithm of 2 with respect to 3. So for counter set is everything is okay. If you think that everything is okay all the time, this is not true. These are specially selected good cases. Yes, when you are a mathematician, or if you use mathematics in practice, you know that almost all cases are bad. There are no good cases. Good cases are created artificially by some wise people. To make a person feel comfortably in this world. Okay. So consider this one very interesting case. I consider K is a sequence 1, 1/2, 1/3, 1/4, and union 0. Right? Oh, sorry. Sequence 0. So we have this sequence 1, 1/2, 0, 1, 1/2, and here we have 1/n. Yes. So let what happens? It's okay. Let epsilon be equal to 1 divided by n squared. I don't understand why it sometimes it doesn't catch. It doesn't see me here, and here it sees me. So let epsilon be 1 divided by n squared. Then we have the boxes of the size 1 divided by n squared cover all numbers from 1 to 1 divided by n minus 1. There will be n minus 1 such non-overlapping boxes. And here we have also n non-overlapping boxes, right? So the number k n of k 1 divided by n squared is equal to 2n minus 1. And if you take logarithm 2n minus 1 and divide it by 2 logarithm of n, yes, and take a limit, then we have 1/2, right? I feel some kind of an irritation looking at that. You have a sequence of points. Each point, oh, I don't understand why it doesn't work. Sometimes, who can consult me how to manage this microphone? So each point has dimension 0, yes, and we have countable union of sets. What? Not always. Sometimes it works, sometimes it doesn't. Okay, so if it stops, you see, sometimes it stops working. Yes. So we have countable set of points. Each point has dimension 0. Each finite number of points have dimension 0, but the whole sequence has dimension 1/2. So this dimension is bad. Why it is bad? Because if we pass to a limit, it jumps. Yes. If you take a countable union, if we have some dimension, then we need to have such formula: dimension of union of an equals to supremum of dimension of an. So good mathematical dimension needs to obey this law, and Box dimension doesn't obey this law, so it is not very good, but it is convenient. We put a set in a box and just count boxes and have dimension in our hands. Therefore, I need to understand the notion of dimension. So, initially there were only integer dimension. A line had dimension 1, a plane had dimension 2, space had dimension 3, etc. Yes? But then there was a theory of integration. Then theory of integration was developed for lines, plane, space, and then Konstantin Karateodori understood how to use Lebesgue integration, how to organize Lebesgue integration on surfaces and curves, on subsets of surfaces and curves. And so he introduced the Karateodori measure, yes, and this gave an impulse to Felix Hausdorff to extend this measure to different dimensions. This happened in 1918, yes, and at that moment Felix Hausdorff was in Greifswald, where Christoph Bandt lives all his life. Yes, okay. So, Hausdorff dimension was invented by Hausdorff in Greifswald in 1918. And now I will explain you what is the Hausdorff measure and Hausdorff dimension. Because box dimension is just a very, very simplified version of Hausdorff dimension. Yes. So first we had the Hausdorff dimension, and then consider a very complicated curve. Consider a curve. How to measure its length? Its length. It's very simple. We take and cover this curve with balls. diameters of balls. Yes? And this sum of diameters of balls gives us some kind of approximation of the length of the line. But this is not very good, because if curve looks this way, if balls are large, then the length of the curve may be 100 times greater than the diameter of this ball. Therefore, we need, from first point of view, we need to minimize the sum of diameters of balls. And second, we need to, at the same time, we need to minimize let their diameters tend to 0. Oh, you need to change the batteries. Okay. So what we do? So let this be curve. Let me denote it by gamma. So length of gamma is a limit as epsilon tends to 0 of infimum of the sum of diameters of balls such that diameter of balls is less than 0 and union of balls contain gamma. Okay? So we consider families of balls of diameter less than 0, yes, which cover gamma, yes. And among all these coverings, we will take the lower bound of such sum for these coverings, and after that we begin to diminish epsilon, yes. So if epsilon becomes smaller, this family becomes more poor, yes. Therefore, this lower bound will rise. So this will be the upper limit of this lower bounds, but since it's monotonous, it's just limit. And it will give us the length of gamma. Very good. If gamma is a curve, so we get this length. Sometimes the length of curve may be infinity. When we have sine of 1 divided by x, then we'll get a curve of infinite length. And suppose we have a surface, some very complicated surface in Rn. Yes? Then we take balls which cover this surface, and instead of taking sums of the diameters, we take sums of the squares of these diameters. multiplied by maybe, so S is P d squared by 4 divided by 4, right? Yes. So we multiplied it by the coefficient and we get this way, we get the area. So this was what Karate-Aderi understood. And Hausdorff began to think why this number should be an integer. This number may be any number, any positive number. Yes. And therefore, he defined two values. I need to, so he defined epsilon alpha dimensional Hausdorff content of K as a lower bound of sums of diameters of the sets UI covering K. Yes, so I will write it K belongs to union UI, right? And diameter UI is less than epsilon. So we take some epsilon more than 0, yes? And we consider the sets which have diameter less or equal than epsilon. Yes, maybe less or equal than epsilon. And among all these epsilon covers, we take a lower bound of this value. When epsilon becomes smaller, this number would grow. Yes, because we take a lower bound of some smaller family of coverings, because each epsilon divided by 2 covering is also an epsilon covering, but not all the epsilon covering are epsilon divided by 2 coverings, for example. So, and we take H alpha of K, it will be the limit as epsilon tends to 0 of H alpha epsilon of K. And it is called the alpha dimensional Hausdorff measure of K. How wonderful it is. So we can consider different dimensions, and in different dimensions we can take measures. But the situation is not so peaceful as this can look from the first sight. Suppose epsilon alpha dimensional measure of K is finite. Suppose we took some set k, it may be fractal, it may be anything, yes, and its measure is some number which is less than plus infinity. Take beta more than alpha, and let us count h beta of k. H beta of k. Oh yes, H beta. So if we take H beta epsilon of k, it will be the lower bound of all sums of ui to the power of beta, and diameter of ui is less than epsilon, right? I don't write that they cover k. It is supposed by default, yes. And we can write it. It will be less or equal. So you see, ui to the power of beta is ui to the power of beta minus alpha multiplied by ui to the power of alpha, right? And this is less than epsilon to the power of beta minus alpha multiplied by ui to the power of alpha. Sorry. Do you see what I write? You see? Okay. Then it will be less than epsilon to the power of beta minus alpha, right? Multiplied by infimum of sum of ui to the power of alpha, right? This value tends to some number m as epsilon tends to 0. But this value tends, well, to 0 because beta minus alpha is more than 0. Therefore, this value tends to 0. If alpha dimensional measure is finite, then on next stage it becomes 0. So we have a very nice picture how it looks like. We can draw a graph. We can see this graph in Falconer's book. So we have this value will be infinity, this value will be 0, and we take some alpha. And so if h alpha of k is finite, then for all greater beta, the beta dimensional measure of k is 0. If we look at this medal from the other side, if h alpha of k is not 0, then for beta less than alpha, it must be infinite, yes. And there is only one value which is on the border between infinity and 0, yes. So This alpha is called Hausdorff dimension of the set K. Alpha is Hausdorff dimension of the set K. This is the definition of Hausdorff dimension. You see, it's very good. This picture. Yes. If H alpha of K is finite, then for beta more than alpha, H beta of K is 0, right? We proved it. From the other side, if H alpha of beta is more than 0, then H beta of K is infinity. Yes, because if it is not infinity, then H alpha of K is 0. So there is only one value, which is the border between infinite value of measure and 0 values of measure. And this value may be 0, may be non-zero, and may be infinite, depending on the case. So we can produce sets whose Hausdorff dimension, for example, is 1, and one-dimensional measure is 0. It is possible. We can create sets of whose Hausdorff dimension is 1, and one-dimensional measure is infinite. Yes? So can we make a set which has Hausdorff dimension, which has a Hausdorff dimension 1 and whose measure is 0? Let us. I will draw. I will create an example of such set. This example will need some further questions, knowing of some further questions, which I will explain later. For example, suppose we have a counter set with a ratio Q. Q counter set. K is QK union 1 minus Q 0 multiplied by QK, right? So IK QK, this is QK, and this is 1 minus Q, it will be QK2, right? So it will create a counter set. Yes. This counter set has dimension logarithm of 2 logarithm of 2 divided by logarithm 1 divided by Q. Yes? Therefore, we can create counter sets of arbitrary dimension. And then we make sequence Qn, which tends to 1/2. Yes? which grows to 1/2, yes, and then we make the following procedure. First, we have a counter set with coefficient q1, then we take a counter set with coefficient q2, then we take a counter set with coefficient q3, etc., right? So the dimension of this set will be logarithm 2 divided by logarithm 1 divided by q1, right? If we take some union up to nth copy, this dimension will be logarithm 2 divided by logarithm 1 divided by qn, right, on n step. If n tends to 0, then dimension tends to 1. Each of these set has 0 one-dimensional measure, yes? The countable union of sets of measure 0 is a set of measure 0, right? Therefore, we have the set whose dimension is 1, but measure is 0. So it is very simple example. It can be created also by other means, but so what is our timetable when we need to? Oh, yes, we have half an hour. Okay, that's good. That's good. I need to remind you some properties of Hausdorff alpha dimensional Hausdorff measure. So first, the properties are properties of H alpha. Yes. Which we need. First, the Hausdorff measure for each alpha, the Hausdorff measure of empty set is 0. It's obvious. Because we can cover by set of arbitrary small diameter. Yes. Then, if A is contained in B, then alpha dimension measure of A is less of or equal than alpha dimension measure of B, right? Then alpha dimension measure of union of the sets AJ, a countable union, is less or equal than the sum of measure H alpha of AJ. Yes. And for any, usually when we consider measure, we consider so-called Borel measures for which all Borel sets are measurable. But for us it's sufficient to know that if we have a Borel measure, then open sets and closed sets are measurable, and all other just follow by by measurability of unions and intersections. Yes. So for any compact, because non-compact sets compact, or and any open set A or any open set K is H alpha measurable. What does it mean the set is measurable? Consider some set A and set K. Yes? If the measure of A for any A containing K, H alpha of A equals H alpha of A minus K plus H alpha of K. This means that K is measurable. If the set is measurable, and if we cut it from other set, then the measure of the set diminished just by the measure of this K. If the set is not measurable, for example, I consider some non-measurable set. Yes? Then it has upper and lower measure. If we erase, then we erase lower measure, and the sum of the measure of this set and this difference will be greater than the measure of A. Okay. So all compact set, all open set, all closed set are measurable with respect to Hausdorff alpha measure. So the Hausdorff dimension is the border between those alpha of which H alpha of K is 0 and those alpha for which H alpha of K is infinity. But you see, how to determine which set has finite Hausdorff measure and infinite Hausdorff measure, because Hausdorff measure is not easy to compute, you see, because we consider epsilon content and then pass to limit where as epsilon goes to 0, we get this limit, and this limit, so I suppose it's not easy to make calculations to find this border, yes? But this question is simplified in some way. How it is simplified? Denote by H alpha infinity of K and the number which is equal to the following thing. It will be lower limit, or lower bound of some ui to the power of beta, or sorry, alpha, so we erase the restriction on diameters, and we get the thing which is called Hausdorff content of K. This value is more easy to find, yes? We just consider different covers and find the optimal cover. Yes, no matter how large or small the sets are, yes? Not very convenient to find, but much more simple than to find Hausdorff measure. So, whereas there is the following theorem. H alpha of k is zero if and of only if H alpha infinity of k is 0. You see? If set has 0 alpha dimension Hausdorff measure, then it has 0 alpha dimension Hausdorff content. Let us compare two definitions. Yes. First I need to notice that H alpha of k is greater or equal than H alpha infinity of k. So if this is 0, then this is also 0. Because both values are non-negative. We have no negative measures. Yes? Right. So this implication is automatical. No. This implication is automatical, right? If this is 0, then this is 0 too. Now suppose I have a feeling that you are tired, a little, but I have no anecdote in my mind at that moment. At that moment, good lecturer pronounces some kind of joke, and this monotonicity of writing and all this thing is erased, and so, but we have just 5 minutes left, or maybe a little more. Yes. So suppose H alpha infinity of k is 0, right? So suppose it is 0. Then what happens? For any for any delta more than 0, there is a family En of sets such that sum of diameters of En, diameters of En to the power of alpha less than delta, right? For any delta, we have a cover of K for which the sum of the diameters to the power of alpha is less than delta. This gives us 0 in the limit, yes? If we look at this sum, then we see that diameter of each, I cannot write E, I write sigma. For any n, diameter of En less than, right? All these values are positive, then each value is less than, each of these values is less than delta, then En, diameter of En, less than the root of delta with the power alpha, yes? So, if epsilon is if delta is epsilon to the power of alpha, yes, then H alpha epsilon of K is less than epsilon to the power of alpha, right? Yes. Also less than delta. Yes. Therefore, so less than epsilon to the power of alpha, yes? Yes. If we tend epsilon to 0, we get that H alpha epsilon, H alpha of E equals 0. Oh, K, sorry. I have E in my scratches, therefore, but then so these two equalities are equivalent, yes. So we can, when we suppose to find Hausdorff dimension, we just look at alpha dimensional Hausdorff content and give us the evaluation of Hausdorff dimension. So maybe at that moment we need to stop our lecture and have sufficient break to refresh our brains. If you have any question, please.